Hello, my name is Martin. Welcome to this video. In this video I'm going to show you a very simple application of deep learning in radiology. We're going to look at chest x-ray images of some of them diagnosed with pneumonia and some the absence of pneumonia. So there's two classes. We're going to look at two pretty simple classification models in Keras. And actually I want to show you what I'm going to show you is based on this guy's kernel that he's sharing on GitHub. His name is Deadskull7, and he has one pretty simple X-ray, a Jupyter Notebook pneumonia diagnosis, and one Inception. So looking at the first one, let me initialize this in my Jupyter Notebook because I already prepared my data and also the Jupyter Notebooks. It's not this one, it's pneumonia. Yeah, pneumonia. Here it is. So we're going to use this notebook. I have to say the data. So the data is all on Kaggle. Here is the data set. What you need is a Kaggle account. With a Kaggle account you can download through the API. To get the API you simply have to pip install Kaggle. You have to also get into your profile under my account and get your API key. So you are authorized to download data. Anyway, we already have this. So I'm going to just load the libraries that we need. I'm going to define the path. We don't need to do the pre-processing of the data because I saved my data as a H5, which is first reload the training and now the test. And we quickly print how many images we have. We have in the training sets 5,216 images and 624 for the testing. And here we believe I need this. Let's hear the problem. Doesn't show up. Let's try again. Here it is. You see a couple of randomly selected samples. On the right side the pneumonia, and on the left non-pneumonia cases. So our task that the model should solve is to identify which one is pneumonia and which one is not. For this, also we quickly make these plots. This one should be, right, quickly, let's give them a little title because this is the training set and this is the title, I believe, testing. So in the training there, both the training and the testing are unbalanced, which means that there is more pneumonia cases than normal cases. This is relevant as the accuracy will not be good. So if you have a simple model that is 100% guessing that a case is pneumonia in 100% of cases, and if you have in your testing, you don't have, well, say you have 80% pneumonia, here maybe 80%, and you're always guessing pneumonia, then you have an accuracy of 80%, which is of course nonsense from a medical point of view, but therefore we just have to keep in mind our dataset is unbalanced, so accuracy will not be a good measurement of the model, of how good the model is. Preparing for the model, we also define a callback to reduce the learning rate on plateau. We define the file where we're going to save the weights, and we import the layers that we're going to use for the model. And here is our model. So as you see, there is only around 10 convolutional layers. We use batch normalization after each convolution, and activation ReLU within the model, and sigmoid at the end. We start off with a kernel of 3 by 3 pixel and work through the model, getting it, I believe, should be around the same throughout. So let's run this. I tried to do more epochs, but it doesn't help, so we set it to 6 because it's quicker, and we train the model from there on. I'm training on a GTX 1070 GPU, which is supposed to be running now. If you do Nvidia SMI, we see that you have, is it not? Yes. Let's log into my, so actually I'm running this on my other computer. I'm working on my laptop, and so I got a workstation with the GTX 1070, and if we run the Nvidia SMI, we got the power usage, and we see that the memory is being used, so everything's fine. It's already in the 5th epoch. We see that the 1st epoch and the 2nd and the 3rd and the 4th, we all saw an improvement of the accuracy. In the 5th, validation accuracy didn't improve, so it skipped saving, and the same for the 6th epoch. So basically we only use 4 epochs for improving our predictions. You can visualize this. So of course, as the epochs advance, the train accuracy, the accuracy on the training goes very high as an indication of overfitting. But as you use the validation accuracy on the test set, certainly, if the accuracy doesn't improve, which you have the case after the third, sorry, this is the 4th epoch, because you have Python wise starting with 0. After the 4th epoch, it doesn't improve anymore, so you throw these. As you see, the model loss in this step, and you get this is for the confusion matrix. You see you get a test accuracy of 74%, which isn't great, but never mind. The interesting part is the confusion matrix. So in the confusion matrix, you basically look at what your model predicts, which is 0 we defined as the absence of pneumonia, and 1 being pneumonia, and the true label being 0 the absence of pneumonia, and 1 the pneumonia. So from a medical standpoint, the interesting part is predicting right those that have pneumonia, so you can actually treat them. What you want to avoid is the ones that have pneumonia but you don't notice it, in which case we have 2 here. We have 2 cases that the model falsely didn't predict that they have pneumonia. And also there is some not so nice. So you have 160 healthy patients which are diagnosed with pneumonia from a model. So this isn't great because you might treat them with antibiotics or whatnot, even though they might suffer another disease or another cause of them showing up at the doctors. What you're going to use, as said, accuracy isn't a good metric for unbalanced data sets, so we're going to use precision, which would in this case is 388, and you have 160 are the false positives, those that you falsely predicted as positive, as having the disease. So you have 160, that's 70.7 precision. And also you can calculate the recall, which is again 388, and you use the false negative. False negative being those that you predicted, that you predict that they don't have the disease, but they do have it. I think that's wrong. Wait, false negative. Confusion matrix. False negative, and you should see it immediately. Here. The false negative are up here. Actual prediction. So yeah, I see it, it's actually 2. So you do get a recall rate of 99%, which isn't bad, of course. Now, this was the simple model. And I'm gonna save this and shut down this kernel. Because what we are gonna do now is having a look at the Inception model that I also prepared. Again, you're going to import the libraries, define the training, and define the labels. Do we need to do this? Not sure. Do it. Pre-processing we don't do because it will take too long. However, we just import the data. Again, the H5 data, and this is the training and the test data. And we don't need to look at the shape. We define the directory again. Let's see some samples again as before. We define the plateau on the learning rate. We define where we want to save our weights. We again import all the layers that we're going to use. And we import from Keras. That's a nice thing about Keras. You can just import these models, and of course Inception model version 3. Let's see. This Inception model is a widely used image recognition model that has been created attention, blah blah blah, on the ImageNet dataset. So it's one of the models that is you can come across very often. Did I run this? I did run this. This is 14. Does it import? It did. And in a minute we should see. Oh yes, important. You need the Inception training weights, which you can get from this guy's kernel. Here it is. You need to download it's not here. Anyway, you can find this file because it's not on his GitHub because it's too large for being on GitHub, but it's a standardized file that you can find all over the internet. And did I import this? Yes, 16. The model definition, and we basically print the model. This is the inception model, and you see it's a lot deeper than what we had look at before. This is what we had to look at before. This now a lot deeper model. We're going to use 10 epochs again, and we're going to train it. And I know this will take a couple of minutes. I hear in the background my workstation, the vents turn on, and it should say that the first epoch, yes, it's training. And I believe I will pause the video quickly. No, actually, I'm going to show you some other things. About radiology, there is one article on Archive from these guys, and it's about deep learning in radiology, an overview of concepts. They published it this year, 2018, and I believe it's a very good summary of what is done in radiology nowadays. Here you see a YOLO. This isn't a classification, this is a detection model, so you can detect various objects, which could, for example, be used for detecting areas of interest. For example, in a brain MRI, does it detect cancers, cancer tumors, or other. Also, there is, now let's first quickly go through this. Practice in radiology, disease detection, and they have a workflow. They briefly introduce you to the terminology and what is artificial neural naturals, convolutions, what are convolutions, and they show you what they do. So first thing, classification, that's what we're doing now. We do it very simply. We only have binary. So we have disease or no disease, pneumonia or no pneumonia, but there could be classification, for example, detection of various disease from pictures. It's a task of classification, and they also always provide sources, who does what, like for example, one pre-surgical brain tumor MRI, or what is it, natural language detection, blah blah blah. Other applications, segmentation, where you basically segment an image into parts of interest. For example, again in brain tumors, you highlight the areas that are of interest, or I believe they also described they would indicate or segmentate white matter for scoliosis patients in MRI. And the third being detection, which is as seen, for example, detecting areas of interest in pictures. Other tasks, image registration, image generation, image enhancement. So they give you a very, very good overview, and they have a ton of sources. So if you're interested, you should definitely refer to this article. Let's quickly see, it's training successfully. Yes, we're already in epoch 7. No need to pause here. We also have, here's again another pneumonia data set, and here the task isn't about detecting, but it's about is it segmentation or detection. And this is actually this year's, the winners were invited to RSNA to present their results. Actually this guy's won. And there's also some kernels here that that should show. Here someone's using mask RCNN. Let's see what how they come up, if there's some pictures. Oh yes. So with this mask RCNN model, they detect areas where specific indication of the disease is visible. So they're training on more complicated model than just what we did now in a minute. Is it done? Yes, it's done. Interestingly, again in our sample, let's see it with the pictures. Open middle voice. Oh, because we saved, we don't need to load them again. And we see the train accuracy improving while the test accuracy doesn't improve. So this is actually an interesting thing. So it saved the weights in the first epoch, and it didn't in all of the following epochs. So this could need some improvement in the model definition. In essence, that we need to change the learning rate, fine-tune some parameters, because basically we were waiting for all 10 epochs to run, even though it only uses the first. And now, again, we're doing a confusion matrix, and it's not a lot better. Why? That's okay. Now I was expecting it to be a lot better, in essence, to have a lot less false negatives. False negatives. Here it has still a pretty many, which is weird. I believe the last time that I run it, so there's of course there could always be changes that maybe I changed some parameter, or the training, which has a random component, doesn't do as well as the previous time. So basically the previous time I had 341 correctly defined and only 49 false alarms that they have pneumonia. In this case now we have a lot more. Is it using the right? Let's import this maybe. Let's try it with this one. And see, yes, this is how it was before. So we have 300, and we have 40. So we have a recall of 88. Again, here what we don't have very good is that we have 90 patients that are sick, that are not diagnosed correctly, which is of course a big problem from a medical point of view. We will also calculate the recall, but I think, I'm not sure what we get here. 3000, oops, we have it a bit high, and is it 90? So anyway, the problem, or the major problem that I believe we have, is that we scale the images to 150 times 150 pixels, while we have a lot higher resolution And I believe if you use higher resolution, and also this would mean that you have to change some parts of the model, basically using larger kernels at one point for taking account of higher resolution. You should have more precision or more accuracy. Yeah, that's from me. It's a very brief introduction of what you can do. So if you're interested, I also have it on. So you have it on this guy's GitHub, and I did it. I put it also on my GitHub, which is reload. Which is here. And I did some changes. I did the changes to the simple model to use batch normalization. Yeah, so if you're interested, have a look. Thanks for watching. See you next time.